free to leave your questions in the chat. So today we'll be talking about system design for recommendation and search. Before that, just one single slide about myself. I'm an applied scientist at Amazon. I work on machine learning for recommendations and search, specifically for books organization. So my goal is to help people find books that they like and read more books. Previously, I led the data science team at Lazada. Lazada was an e-commerce startup in Southeast Asia. It got acquired by Alibaba in 2016. And then after that, I went to join a health tech startup where we worked on early detection of preventable diseases, healthcare resource allocation, all that good stuff. And now I'm in Amazon. So if you want to find out more about me, you can go to my website if you want to. But now, pay attention to this because a lot of my slides are going to be images with very little explanation. So the key is really in what I say. So the topics. We're going to go through 4 large sections today, of which 2 are key. First, we'll talk about context. Well, we talk about batch versus real-time recommendations and why we use each of them. Then after I take you through the system design, I'll split it into a 2x2 of offline versus online and candidate retrieval versus ranking. And then we look at a couple of industry examples from Alibaba, Facebook, and DoorDash and how it fits this system design paradigm. And if there's time, and I'll rely on Chester to tell me if there's time or not, we'll go through a very quick example of how to build an MVP. So context, batch versus real time. So I'm sure most of you are somewhat aware with batch. So this is batch versus real time in the case of analytics, right? In batch, you collect data every 2 days, you update your dashboard every 2 days. In real time, you collect data and you update your dashboard in real time. It's the same for recommendation systems. In batch, we generate recommendations every 1 or 2 days. We store them in a recommender. In this case, it would be a key value store like Redis. So, and these recommendations are refreshed periodically. It could be 1 or 2 days, every 1 or 2 days, or every 1 or 2 weeks. In real time, it's slightly different. Your recommender is now some kind of endpoint. It could be REST, it could be gRPC, etc. And the recommendations are generated in real time, in the sense that when a customer logs on, as the customer is browsing different detail pages, the customer likes an item, the customer likes a Twitter tweet, or a customer likes a LinkedIn post or on Facebook, you refresh, you quickly, based on that input, you understand what the customer likes and update their recommendations in real time. Why do we want to do this? Why do we want to do batch? Well, no, batch has a lot of benefits, right? It's pre-computed, and in general, it's computationally cheaper, right? You only need to generate it once a day, and it benefits from economies of scale. And then once you generate it, you can just cache it in a key value store, where the key is the customer ID or item ID, and the values are the recommendations. And key value stores today, they are very, very robust, very, very scalable, with many providing 99.9% uptime. So if you just put everything in the key value store, this reduces ops burden on the team. And such as on-call alarms and alarms go offline because you can rely on a very good key value store. And it's much simpler because you decouple the computation of recommendation from the serving. So what this means is that, hey, every 1 or 2 days or every week, you gotta kick off maybe a large Spark job that computes all your recommendations for everyone and every item. And even if this computation fails, there's no customer facing impact, because all your recommendations have already been generated, are already available in a key value store, and you always will have recommendations. Well, they might be a bit stale, but that's fine. There's no customer facing impact. And only once maybe your Spark job is completed, then you update your key value store. So in that case, we decouple computing the recommendations from serving the recommendations. And even if the computation fails, you just serve the previous batch of recommendations instead of an empty slot, which reduces conversion rate and revenue. So batch recommendations sounds so much simpler and so much easier, right? Why do we want to go real time then? Well, for real-time recommendations, you require a lot more compute. So for example, to support such a system, you need to be able to aggregate streamed customer events. So what does this mean? If you say that, hey, a customer has just logged on, she's looking for shoes, and as she types a search query shoes, she clicks on shoes, heels or boots or hiking boots or whatever. As she clicks on different shoes, you want to update her recommendations for her on the homepage immediately. This requires you to have the ability to process all this near real time, all this in near real time, maybe in seconds or maybe minutes, to have this. And then with each customer event, you might generate new recommendations. So for example, if I'm a customer and I'm usually buying electronics or books, my homepage recommendations will have book and electronic recommendations. But let's say tomorrow I'm intending to go, no, not tomorrow, next week, I'm intending to go hiking. And I need hiking boots, which I don't have. And I'm searching for hiking boots in the morning. I don't find what I want. And then maybe in the afternoon when I come back, ideally would be nice to have my homepage recommendations update to show hiking boots, because it knows that that's what I'm interested in. So that's the reason why, because all this is responsive to the customer. What I'm talking about is the customer mission. It has to be responsive to the customer mission, in the sense my mission for right now, my usual mission is to find books and is to find electronic gadgets. But my mission right now for the next 1 or 2 days is to find hiking boots. And second, real time, and the big benefit of real-time recommendations is that it allows us to serve cold start customers. So that cold start customers are customers that we don't have data on their past purchase, or we don't know what they're interested in. This is a customer that's completely new, has just created an account and is going to start shopping on our platform. How do we create recommendations for them to discover products in real time? Well, if we can generate recommendations based on their very first detail page view, or their very first like on a product, we can generate recommendations for them. Customer comes in, we don't know what gender, what age group, whatever this customer is. If the customer starts searching for dresses, we sort of can guess, hey, it's a female, or the gender is a female, shopping for a female. It could be a husband shopping for a wife for dresses. It doesn't matter. Or if the customer starts searching for electronics, we know that the customer is interested in electronics, and we can surface electronic recommendations on the homepage. And this same goes for YouTube. I might be searching for coding. This applies for, and this same paradigm of real-time recommendations apply not just for e-commerce, but for several other domains as well. For example, travel. Our vacation destinations are often changing, and it's unlikely that your past travel location is a good signal for recommending your future travel location. Same goes for YouTube. In the day, I might be searching for coding tutorials to solve a problem. I might want an exercise or yoga video during lunch. And I might want recipe videos for dinner. So this is the time-sensitive context on it. And then the other big part is that, every day we create recommendations for so many customers, right? Personalized user to item recommendations, but how many of those customers actually visit our website? I would say it's not a very big proportion of all the customer recommendations we generate. Therefore, by only creating recommendations for customers who actually visit the site, who actually need them, it's a very efficient use of your compute and serving. So at this point, I hope that you sort of understand the rationale between batch and real-time recommendations, and when to go for which. And in this slide, in this talk, we are going to be focused on real-time recommendations, aka on-demand recommendations. I see that Chester has showed up. Is there a question?
Yeah, I think before you switch to the next, the dive into the real-time, there are 2 questions related to it. I hope I can ask now, or you want.
Yeah, sure.
So I think that one of is the batch really cheaper because you're pre-computing the user regardless whether they are, they're using your service or not. So you mentioned that before, but you want to.
That's a great point. That's a great point, and I try to mention it in real time as well. Yeah.
So the other question is how batch is useful for guest users. You also touched this. They visit and go if they do not find the recommendations.
For guest users, so if the user is a guest user and the user is not logged in, we might be able to create, maybe for this guest user, we don't have any guest ID. We might create a guest user ID, or we might create a session ID. But the fastest we can respond is maybe the next day, where we create recommendations for this guest user ID or for this session ID. So it's not going to be responding as responsive. And that's why real-time recommendations might be more appropriate there for guest users. All right, so this is real-time recommendations. Next, we're going to very quickly go through the system overview. And I'm trying to simplify this to break it down into two axes, but tell me if it's oversimplified. So I think that it's useful to think of it in terms of online versus offline environments. In the offline environment, we usually still have the batch processes. In real-time recommendations, it doesn't mean that we don't do any batch processes. We still do have batch processes, but when we're serving it, it's mostly online. So in the offline environment, our batch processes will include model training, creating embeddings for our catalog items, building our feature stores, building our indices or knowledge graphs. And then in the online environment, we then use these artifacts to serve individual requests, to serve recommendations for search or anywhere else. And usually, these artifacts are loaded into memory on CPU optimized servers. Next, we talk about retrieval versus ranking. Usually, retrieval is a fast but coarse approach. So what we do is that we go through millions of items in our catalog and we quickly pick out hundreds of candidates, hundreds or maybe even thousands of candidates. And what we're trying to do here is that we trade off precision for efficiency. In this case, we reduce the search space from millions of candidates to hundreds, right? That's a 99.99% reduction in the downstream ranking task. Most retrieval methods, and that's what I'll be talking about in this system here, convert the input item or the input query into an embedding before using artificial nearest neighbors to find similar items. Nonetheless, we also see examples by DoorDash where they use a graph. On the other hand, ranking is a slower but more precise approach. So what this means is that we are processing fewer items, right? So we have hundreds instead of millions. And therefore, we can also add features that would have been infeasible in the retrieval step. So in the retrieval step, we're usually only just using a single embedding. And you can consider it as a single feature and then retrieve maybe 100 or maybe let's just say 1,000 candidates. In retrieval, we would add features, right? We add features about the candidate category, the candidate price, previous click-through rate, previous purchase rate, and we use that in our ranking model. And our ranking models can also be more sophisticated. It can have more layers and more parameters because we have more time to rank each of those items because we're only working on hundreds of candidates instead of millions. Usually in ranking, it's usually modeled as a classification or learning to rank approach. Classification is more commonly seen, and the examples we see, they'll be using a classification approach. Learning to rank approach is not as commonly seen. Personally, I've used it. It doesn't work as well as simple classification. Specific classification, there can be two types. One type is whereby a customer comes in and the final layer is a softmax of maybe the 10,000 most popular items. And you try to rank whether a customer is likely to click on any of these 10,000 most popular items. This is a fixed output layer where you only have the 10,000 items. The other approach is whereby the input is the customer and the item, and you try to rank the probability of click on that customer item pair. And so this is more flexible in the sense that you can have new items coming in all the time and you don't necessarily need to change the model architecture. And so here's how the axes come together. In offline retrieval, we use the training data to train an embedding model. So this can be something like self-supervised approach, such as representation learning, and we'll see examples of this later. And then you can use embedding models such as word2vec, or it could be a supervised approach that predicts the probability of click. And then you just chop off the head and use a penultimate layer to embed your items as well. So with this embedding model, once this embedding model is trained, we can embed items from the catalog, index these embeddings within some kind of approximate nearest neighbors, which you can then look up for candidates. In offline ranking, one thing we do is we load our item and user data into key value stores or feature stores that allow us to quickly retrieve user and item attributes to augment our candidate data. And we use this to train our ranking model. One thing to note here is that it is ideal to use the same feature store in both offline training and online serving. So this ensures that you minimize train serving skew, right? Whereby your offline data is different from your online data. We might also need to do time travel. Time travel is an aspect whereby you need to travel back in time to get accurate point in time features. For example, if we're looking at it right now, you might see that this customer has bought hiking boots right now. and if you're training a model right now, but back then at that point in time, he didn't buy hiking boots yet. He was looking for hiking boots. So you need to time travel to get the state of the item and the user at that point in time. So once you do this, you train your models, you train your features, you get a couple of artifacts. And these artifacts will just be used in the online environment. So in the online environment, when an incoming query comes in, you use that same embedding model that you use to embed all your catalog items to embed that either that input item, if a customer is on a detail page view, you embed that detail page view product ID, or maybe you have an embedding model that is a two-tower embedding model that embeds both items and search queries. Use the embedding model to embed the search query. And then given that embedding model, now you can use your approximate nearest neighbors to retrieve your top K candidates, right? This could be top 1,000, top 100, whatever. Now that you have a set of candidates, maybe 1,000, we can then pass them to the ranking stage. And in the ranking stage, we add features to the candidates using our feature store. And then with the candidates, they are augmented with the features. We can then rank them with the ranking model, that optimizes for certain things like click-through rate, conversion, before finally reordering the results and showing to the user. So this is how it looks like overall. In terms of system design. So now that we have an understanding of why we might want real-time recommendations and what the system design looks like, I mean, we can now look at some examples of how this is implemented in certain industries, in certain companies. Oh, Chester has a question.
Yeah, there are a few questions related to that. I thought maybe before you jump to the next topic. So the first question is, so for retrieval, it can be with a multi, this is more like a comment. For retrieval, it can be with a multi-recall strategies. And we do the first layer rank and the merge, and then we feed them to the re-rank model. So this is from Luis.
Yes, that's correct. I think in how I depicted it here, I only showed a single stage of retrieval and a single stage of ranking. Nonetheless, some companies have done it fairly in a fairly sophisticated manner, whereby there's multiple stages of retrieval and ranking. It could be usually retrieval is just a general retrieval stage, and then there's a ranking to rank everything, and then you might have there's an intermediate ranker, usually a student-teacher model to speed it up to further trim it down, and then maybe there's a final ranker, the full model, and you might have other objectives that you might do re-ranking on, such as, for example, you might re-rank to ensure diversity in your recommendations and in your search results, or you might re-rank to introduce new items. So yeah, it usually is a cascade approach in industry.
Got it. And the next one is a question from Dave. He said, is there such a thing as a recommender that a user to have some control over what is recommended?
That's an interesting point. I think in industry, we try to give users control of the recommendations. So one way, and you can see this, is you probably see this in Twitter and LinkedIn, like you flag something, I don't like seeing this. I think Twitter lets you select tags that you're interested in, and they probably use that to recommend you tweets to see as well. So that's one way that you can, whereby you can select tags to demonstrate your interest. For example, I might be interested in data science and machine learning, so I might have those tags. I might not be interested in, I don't know, stock market, and I would deselect them. I would say I'm not interested in it. So the Twitter algorithm will try to show me tweets that are closer to data science and machine learning, and maybe further away from stock market, things like that.
So the next question is, how do you evaluate the performance for the retrieval models?
Yeah, the retrieval model, that's a pretty tricky question. So for ranking, that's a very tricky question in terms of, because the retrieval model is split from the ranking stage, right? Whatever you retrieve may not be finally shown to the customer in that particular order. So what I've seen in most papers is that they continue to use the same approach. They use a recall at K approach, which is given the top 100 candidates that we've retrieved, how many of them ended up being clicked on or being purchased. Even though part of this is dependent on the final ranking model, but you can sort of see that, hey, given the the candidates that we've retrieved, how many of it did the ranker judge to be good enough, and how many was presented to the customer, and how many of it eventually got clicked on. Another aspect of it is, yeah, it's usually your standard recall and BCG metrics. Yeah, that's as far as I can think of.
Okay. And okay, we could probably just pick another two and let you move on, and then we can leave the other questions later on. So are the generated artifact the key value pairs?
Pardon?
Are the generated artifacts, all the artifacts, are they key value pairs?
No, not necessarily. So the embedding model is you can think of it as a deep learning model per se. Okay, so the embedding model could be a key value pair whereby you pass in a product ID and it returns a product embedding. There are some cases where this would not work in the case of search queries, whereby you need to pass in the search query. That search query needs to be parsed and tokenized and cleaned up before it returns a query embedding. So the embedding model could be a key value pair in the case of item IDs, but in the case of search queries, it cannot be. The approximate nearest neighbors index is not a key value pair. It's not something whereby you pass in. It's not something whereby you pass in an embedding, right? Because the embedding that you get, there's so many different permutation and combinations of it. It might not necessarily just be an embedding of a single product ID. It could be multiple product IDs that you combine together, sum it up over some weighted average that you use to find the embedding. So this is definitely not a key value pair, and it's more likely some kind of approximate nearest neighbors index, which we will see some examples later. The feature store, this can be a key value pair, sort of a map, right? Whereby given a user, what are the different attributes of the user, the spending propensity, the gender, the estimated age, etc. So this can be a key value pair. Whereas the ranking model is not a key value pair. It's more likely the input will be passing in pairs of user ID and item ID. And then you go through the ranking model, probably some kind of deep learning model. And then the output would be the propensity of click or the propensity of purchase. And that's how you score it.
So there are a bunch of other questions I probably just want them to you answer later because I don't want to interrupt the flow of your slides. Okay, I'll read them later. Okay.
I think we're about halfway through, so we can try to finish it before we go to the end. Yeah. All right. So next we'll go through some examples from industry. So we start with Alibaba's approach for creating item embeddings for candidate retrieval. So in the offline stage, what they do is they say they use logs. So what this is these are session level user item interactions. So they mine it to create a weighted bi-directional item graph. So what this means is that, hey, you take all the things that I've clicked on, I've purchased in a session. Between every item, I calculate the propensity of transition between every item, and I use that to construct my graph. Then with my graph, I can then create item sequences via random walks on the graph. With this, we can then create item embeddings through representational learning. So the approach that they use was the word-to-vec skipgram. And this is a pretty smart approach because it does away with the need for labels, right? You don't need labels at all. It's very easy to generate such sequences. And then finally, with the item embeddings, they get the nearest neighbor. I think that's what they do. It's not very clear in the paper. They get the nearest neighbor and they store it in their item to item similarity map. So what this means is that given an item, find other similar items, right? Then, so once this item to item similarity map is generated in the online environment, when the user launches the app makes a request to the Taobao personalization platform, TPP. So what this does, it starts by fetching the latest items that the user has interacted with, which you don't see on the diagram here. So what are the items that the user has previously purchased or interacted with in the previous session? So from those items, I retrieve candidates. Given any item, I could probably retrieve 100 or 200 candidates from them, and these candidates are then sent back to TPP. So once TPP get these candidates, it sends it to the real-time ranking service platform, RSP, and this ranking service platform ranks it via a deep neural network before returning a ranked list to the user. So you can see some very familiar components in here. The I to I similarity map is really just the candidate retrieval, and the ranker is really in the form of the RSP. And of course, the embeddings are trained via random walks, word2vec plus random walks on the item graph. And again, you can see that they separate it into the offline and online environment as well. Alibaba also shared a similar example where they apply a graph network for ranking. So in the offline environment, they do a lot of things. They combine an existing knowledge graph with user behavior, such as things that the user was impressed but not clicked on, and item data to create a adaptive knowledge graph. This is a graph for user and item. And then this is merged with other user data, such as demographics, user item preferences, to train the model. And this model, ATBRN, is Adaptive Target Behavior Relational Graph Network. So it's a mouthful. I'll just call it a model. And then in the online environment, you can see coming over here, given a user request, first, the candidate generator, which they didn't discuss about in the paper, the candidate generator retrieves a set of candidates and user ID before passing it to the real-time prediction service. So you can see the candidate generator will return a set of item IDs for the ranker to rank, as well as the user ID, which it's used to retrieve user profile. So at this stage, with the item ID and the user ID, they call their feature stores to get the item attributes and the user attributes, send it to the real-time predictor. And of course, part of it is that they also need to call their graph engine, which relies on their historical user behavior. So all this, the graph representation of the item data, the item attributes and user attributes are then sent to the ranker, which then predicts the probability of click on each candidate item, which gets the recommended results. So the key response is whether the user clicks on the item or not. And this is then fed back into the feedback loop for logs. So over here, again, we see very similar things. In the offline environment, they build their graph in the offline environment and train a ranker there. And in the online environment, here's the candidate retrieval, here's the ranker, and here are the feature stores that they use. Next, we look at something slightly different. We look at Facebook's approach to using embeddings for retrieval in search. So it's specifically for retrieval. So in the offline environment, which is the right half of this image, they first train a 2-tower network. So this is not including an image, but you can see that they train an embedding model so that the embedding model is a 2-tower network with a query encoder and a document encoder, basically a query and a Facebook group or Facebook profile encoder. That outputs the cosine similarity for every query document pair. So this is not shown in the image. You can go visit the actual paper itself to learn more about this 2-tower network. So this 2-tower network ensures that search queries and documents are in the same embedding space. So right now, they're just going to use the document embedding model to embed each document, and they do this via a Spark batch job. So basically, given a document embedding model, given all the profiles, all the groups, all the whatever pages there are on Facebook, they embed each document and they store it. So they store it in 2 ways. One way is they quantize it and publish it into their approximate nearest neighbors index, and this index is based on FAIS, which is Facebook AI Similarity Search. Is a approximate nearest neighbors framework, and then fine tune. And then the embeddings are also published in a forward index without quantization, and these are used for ranking. So in the online environment, what happens when a query first comes in? When a query first comes in, it goes into query understanding. So these are a bunch of rules to sort of understand, annotate the query. Hey, is this a person? Is this a location, etc.? Is this a group? And part of it goes into embedding inference, which relies on the query embedding model. So one thing to note, the document embedding model and the query embedding model is actually just the same model, but 2 separate towers. So they use the query embedding model, given a search query, they embed the query in the same space as the document, as all the documents have been embedded. What this allows them to do is that given a query embedding, they can find similar documents, right? Then over here is the standard retrieval approach. So you can see the retrieval, they use this inverted index, which is their approximate nearest neighbors index. And then after that, they pass it through ranking, and then you get end results. And over here, you can sort of see that they've roughly split it into the offline environment and the online environment. So everything here is generated in the offline environment, which gets pushed here, and here's the online environment. And we see our familiar stuff. So feature store is part of the forward index. And of course, there's the ranker and there's the retrieval, which I won't deliberately call it out. But you can see they train the retrieval and the ranking model offline. As a final example, we look at DoorDash. So DoorDash has a fairly interesting approach. They don't use at least in this article, they don't use approximate nearest neighbors. They use a knowledge graph for query expansion and retrieval. So in the offline environment, they train models for query understanding, query expansion, and ranking. So you can sort of see this here, it's all grouped up into the ML service. This is their knowledge graph, and Elasticsearch is what they use to retrieve similar items. And then they also load, they load all these documents into Elasticsearch for using retrieval, and the attribute data is loaded into this thing they call the search DB. So what this does is that given a final set of items that you want to show to the user, we would augment it with, we would add attributes such as ratings, price points, the item tags before we show use to the user. So in the online environment, what happens is that each incoming query is first standardized. So they standardize it via applying simple spell checking, and they also apply synonymization via a manually curated dictionary. So what this means is that Kentucky Fried Chicken will be the same as KFC or Kentucky FC, etc. These queries are then go through query understanding, right? And what this does is that it also goes through the query expansion. So for example, a query for KFC will return tags such as fried chicken and wings. So based on these tags, which are created in via their knowledge graph, again, you can go through this link here to understand more about the knowledge graph. But the knowledge graph, essentially, given every restaurant, they find similar tags. So the restaurant KFC will have similar tags for fried chicken and wings. And then given these similar tags, what are other similar restaurants? So restaurants that apply to tags of fried chicken and wings will include things like Popeyes and Bonchon Fried Chicken. So after this, so with the query expansion, they get more candidate restaurants, get more candidate food items. And then these candidates are then ranked based on lexical similarity between the document, the query and the document. The document in this case means the restaurant and the food item. So for example, if I'm searching for Kentucky Fried Chicken, clearly KFC is going to rank first. And then for other restaurants, given all their menu items and the description, what's the lexical similarity between fried chicken and what the restaurants serve? They also include aspects of store popularity and possibly the search context, such as the time of the day and the location, right? So location is important if the restaurant that you want to order from is not available within your radius, that's clearly excluded. And of course, the time of the day could matter in terms of whether you're ordering breakfast, lunch, or dinner. And of course, they have offline. Part of it is they have offline evaluation, which they do before before deploying new models. And over here, we see same things, same familiar components, the knowledge graph in place of a feature store, or in place of the approximate nearest neighbors for retrieval, and that's how they use it for expansion. And of course, they have the ranker here. So I'm at this, now that we sort of know, oh, sorry, Chester, yeah.
No, it's, I don't know, it's a good point to answer some of the questions. You got plenty of time, so don't worry about the time.
Yeah.
Okay, so I'm just going to pick up the few questions here. Now, every question will be addressed. I just want to make sure that the recent one got answered. So I'm going to start with the last one. So you mentioned that the idea of the user select the text to demonstrate interest. What do you mean by this? And please explain the UI for this approach. So this is coming from Dave.
Give me a second, and I'm gonna go to Twitter. I hope it shows up on my profile. I see this all the time. Okay, great. I want to share this page. Share. All right. Are you able to see my?
Yes.
Are you Safari? So you can see topics to follow. So you can see, you can sort of choose, you want to follow data visualization, UX design, smart technology, keyboard enthusiast. So by selecting these tags, you indicate interest in this kind of topics. And that's how the recommendation system understands your interest. And I know Tencent has a similar recommender for news, where we can indicate interest in topics such as politics, sports, I don't know, COVID, economics. And based on this, Tencent will personalize the news recommendations that it gives to you based on the text that you've indicated interest on.
Okay, so that's the question from Dave. The next question from Luis is that is why not use U2I, the user to items, in retrieval, but I2I retrieval in Alibaba example?
I'm sorry, could you repeat that again? Why not use U2I?
Yeah, that's maybe I can, I don't know, I can enable his he talk himself. So, but it's the literally the text was saying, why not use U2I, user to item in retrieval, but I2I retrieval in Alibaba example. I assume that is using I2I in
I see.
Yeah.
I understand. Yeah, so in this case, I think in this example, we're using an item to item similarity match, right? Whereby given the user trigger item to item. I think in this case, you can actually think of it as it's both U to I and item to item. So why do I say that? Because given a user coming in, right, TPP, the Taobao personalization platform, will use the user trigger. And what do they mean by user trigger? It means that what the user has previously browsed, what the user has previously bought, previously liked, previously wishlist, and use these items to find the item to item similarity map. So what this is doing is that it's trying to find items that the user has previously interacted with, demonstrated interest for, and then use those items to find other similar items. You're right, they could also do something completely separate, whereby given a user ID, try to retrieve a pool of candidates before ranking it. That can be done as well. So I think it can be a mix of, there's no right or wrong way, and either can be adopted.
Okay, there are two, three general questions. I'll leave that to the end, so you can. I'll let you continue.
All right. So the final aspect is actually fairly fast. I just want to very quickly go through. How to build an MVP. So for our model, so I'll just go through the high level steps of the key ingredients that you need for MVP. So firstly, if you need to build an MVP, and the system design approach that we've gone through largely relies on embeddings, and all the examples we've gone through largely relies on embeddings. Alibaba uses embeddings, Facebook uses embeddings for their search. So we're going to use something very similar, which is called self-supervised representation learning, or in other words, it's also called word-to-vec. So it's very simple. In Instagram's example, they learn account embeddings by taking all your likes that you have liked in chronological order, and they just sort it, right, in chronological order. And then based on this, you can learn the account and the context. And this is the word-to-vec approach. This is the key, this is the main word that's in the middle, and these are the context words. So given the main word or the context word, you try to predict each other. So they use something similar to in what they call IG to vec, Instagram to vec. Uber also does the same thing for search queries. They consider every search query, which is the top row here, as the keywords. So, and then you can sort them in a sentence, right? And the queries are next to each other in the sentence if they were purchased, if those queries led to the same purchase, led to the purchase from the same restaurant. So in this case, these are the keywords and this is the context. Therefore, they apply a GLOVE-based model. So GLOVE stands for Global Vectors for Word Embeddings. It's an NLP approach from Stanford. Again, this is a self-supervised approach whereby, hey, you just use what people have. Okay, it's not exactly a self-supervised approach. You do sort of need some kind of labels in terms of what they purchase on as your context. But this is not difficult. You don't really need to create positive or negative labels. As a final example, we go back to the Alibaba example, whereby they use user interactions to learn item embeddings. This is the first example I went through in the industry examples. So you can see that they have all these user behavioral sequences. They sort them in a sequence. and then they compute the transition probability from A to B, B to C, etc. And they use it to build an item graph. Then after that, they just apply random walks on the item graphs to generate sequences of a certain length, maybe length 100 or length 200, and then they just put it through standard word-to-vec with skipgram approach. So this, I really like this approach. Why? I really like self-supervised representation learning in general, not just this specific Alibaba approach, because it's self-supervised. I don't need labeled data. And the problem with using labeled data, that's very difficult. It's not getting the label, it's getting the labels, but not the positive labels. It's actually very difficult to generate good negative labels for your machine learning model to learn from. And using self-supervised representation learning, you completely do away with it. Of course, using a supervised approach, you can get better returns, you can get better outcomes on candidate generation. But if you're starting from scratch, I highly recommend you adopt the self-supervised representation learning approach. And then, so once we have all these embeddings, we can apply approximate nearest neighbors. So why do we need to use approximate nearest neighbors? Well, because exact nearest neighbors is going to be very slow, and we don't need that precision in the candidate retrieval stage, right? So approximate nearest neighbors, it trades off accuracy for speed, and there are several approximate nearest neighbors open source implementations, such as Google's scalable nearest neighbors, Facebook AI similarity search, and hierarchical navigable small world graphs. So I ran a benchmark on these three algorithms using the GloVe data set, 100 dimension embeddings. And then to mimic production conditions, each query consisted only of a single embeddings, batch size 1. Sometimes you'll see benchmarks where the batch size is 100 or 1,000. Yes, sometimes if your online production environment, you group them into mini batches, you can benefit from this. But to keep things simple, I just kept them at a single embedding batch size 1. Then after that, I built and queried approximate nearest neighbors indices and to tweak several parameters, right? It allows me to trade off speed versus recall. So on the y-axis over here, we have queries per second. Of course, the higher is better. The higher means the lower latency on our query, the more, the lesser instances we need. And the x-axis here is the recall. If we get recall of 1, that means that it's as good as exact nearest neighbors, which is ideal. But even if it's not, it's not the end of the world because we don't need the precision. So ideally, we want everything to be in the top right corner. So top right is better. And in this graph, you can see that scan outperforms the other two items in terms of latency and recall. So this is something, if you're thinking of doing this, try to do a benchmark. If not, just use scan. One thing to note about the Facebook framework is that it's built for batch and not optimized for individual queries. So that's why it's not doing so well here, but it is very fast in batch. So for ranking, I recommend just start with simple logistic regression. I mean, if you want to make it more fancier, you draw some image like this, and this is actually now a neural network and just a very shallow neural network. As input, we have user features and item features. User features could be like propensity of past categories. For example, is this person, what categories does this person usually buy? Could be fashion, could be groceries, could be electronics, could be furniture, books, etc. And then, what's their price propensity, what's their gender, what's their age, what's their location, etc. And then item features would be, historical click-through rate, historical purchases, what the category of the item is, etc. So you can have a lot of features, and then I haven't even included context features and cross features in here. But generally, just try to start simple and make it a bit more complicated when you need to, because that way it's easier for you to build a strong foundation. And the final layer is really just this is a classification approach where you just predict the probability of the of interaction. And interaction here could be either the user clicking on it, or the user liking it, or the user purchasing it, or the user clicking and viewing the search result, right? So and so with this, you can then rank, hey, given that user and given all these candidates, this 100 candidates, what's the probability of click or purchase? And then you just sort them based on that. Finally, to serve this, we would just use multiple instances and a load balancer. So this allows us to easily scale horizontally. So each instance would contain their own retriever or own ranker, and this is also how I can't remember, I think it was JD. This was also how JD serves their models in production, where every model and instance is its own machine. So this allows us, so you can easily scale horizontally, right? Because each machine is just generic, it's replaceable, it's fungible. You need more throughput, you have more traffic, you just spin up more instances. And then you just have a load balancer in front of it, in front of all these servers to direct traffic accordingly. Beyond traffic, the load balancer can also have multiple other purposes. For example, blue-green deployment. For example, we might want to refresh our models daily, but how do we do this in a safe approach? We have our existing fleet, we call it the blue fleet, and then to do that, we will spin up a new fleet, we'll call it the green fleet, and we would direct traffic, maybe 1% of traffic to the green fleet. And we check the metrics. Hey, is latency fine? What are the click-through rates, if you're able to measure click-through rates on the fly? And then you gradually increase the traffic 1%, 10%, 50%, 100%. And that gives you safety of the green fleet, right? If let's say at 1%, you direct traffic or 1% to the green fleet, and latency is very high, maybe above 200 milliseconds, something is wrong with the green fleet, and you just shut it down and you just continue serving traffic to the blue fleet. So blue-green deployment gives you a lot of safety, and that's what the load balancer can do. The load balancer can also be used in A/B testing. For example, a user coming to a site can be assigned to different treatment and control groups. So treatment and control groups would just be different fleet, right? There could be a treatment fleet, there could be a treatment 2 fleet separate. And then what your load balancer does is that it can just direct traffic based on all these different instances that you have. So all this can seem very complicated. An easy, simple approach is just to use SageMaker. I mean, this is not intended to be an advertisement, it's just that it has pretty good latency and throughput, even up to thousands of requests, close to 10,000 requests. And it handles blue-green deployment and A/B testing out of the box, and it really reduces a lot of development effort. So that's the end of my talk. If you want to stay updated on what I'm doing, you can find me on Twitter and LinkedIn via Eugene Yan. I also write a bit, and I share my speaking on my site. And once I get a recording of my talk, I'll share it there and send it out to my email list. So that's all I have, and thank you.
Great talk, Eugene. I'm just continuing with a few questions here. The question is for the Alibaba graph, are they simply counting the frequency of the items pair appearing in the user log? So in sequence. So this is a question from Matt, from United Arab Emirates.
Yeah, I think yes, it's counting the frequency of the items applying together. But one thing to note is that this graph is a bidirectional graph. So it counts the frequency of people viewing B after they view A, and people viewing A after they view B. So there are two different transition probabilities here.
Got it. So let's answer some of the few questions asked earlier, but we didn't get a chance to ask them. So okay, how recommendation is possible in offline device with low resources?
I have never had to do that before. I would say that. Okay, I would say that. Let me try to imagine this. Let's say I have an app, and this app currently right now is offline. It could be there could be an approach whereby every time the app is online, the app would fetch the most recent recommendations for me and cache it within the device itself. And if the app is offline, it will continue to just use those old recommendations or old search results. This is what happens for low resource devices. This is the approach that you would use. You might use is in areas like Southeast Asia, where Wi-Fi connection and mobile data is expensive, and we don't want to continuously be refreshing our recommendations for users on the fly. So we just periodically cache those recommendations, as well as periodically retrieve the logs whenever the user goes online. So that's something I can do, but I don't think it'll be real time unless you're able to embed a model within the app itself that regenerates this recs on the fly. There is one approach I've seen that does this, and that's how Netflix shared an example of how they actually perform the ranking on the user TV, whereby the candidates are all cached and therefore will not change. But I'm just trying to find it. Give me a second. The candidates are all cached and will not change, and it updates in real time based on how the users browse on the website. So that could be something that if you're doing this, you might want to consider it. I'm just gonna share my. I'm just gonna update my screen to share it. Now, share. All right, yeah. So yeah, re-ranking is carried out on the client device, so it doesn't do any round trip to the server. So what it does is that all the candidates are, or rather all the different widgets, the different widget rows are all on your device, and re-ranking is carried out on the device itself. But this means that the set of candidates are all fixed, right? Yeah.
Okay, so the next question is, how have you handled the position bias?
That's a good question in terms of handling position bias in recommendations of search. I've seen two approaches that have been used very frequently, and I'm gonna try to refer to one approach that I really like, which is how Spotify did it. Yeah. Did I? Yeah. So what they do is that they apply sample re-weighting. So what this means is that in production, your items will not be impressed to the users at the same rate, right? So based on this, things that are already shown, if you just measure the absolute number of clicks, they would tend to rank higher or show up more in the recommendations. So what they do is they apply sample re-weighting in the sense that they ensure that they reweigh the samples so that they are somewhat to account for the non-uniform probability. So essentially what it means is that, hey, for samples that are shown more, we downweight them so that we normalize it. And for items that are shown less, we sort of increase the sample to sort of make sure that it sort of aligns whereby the probability of view is shown. So instead of predicting probability of click given item, it is now predicting probability of click given item given impression. So that's one way to do it. The other way to do it, which I've seen in the Google rules for machine learning, is that when you're ranking a model, you would include the position of that item in the candidate retrieval. So what this means is that, hey, you have a set of items, and you're gonna when you're training the model, you say, hey, this item was ranked 1, 2, 3, 4, 5, 6, 7, and what's the probability of click, right? So what this means is that the model learns that, hey, learns the relationship between the rank of the item and the probability of click. So how does that control for bias? Well, in production time, you would fill this column with 0 and give all these items a 0 rank, so that they are all the top rank. And that's how you would exclude the position bias, right? The position bias is no longer used in the model to learn on.
Great. So the next question is, you briefly mentioned a student-teacher model as an intermediate model. Could you please explain a little more about how this works and where does the teacher come from?
That's a good question. I want to try to find a GIF that I have that explains this very well. So this is how Facebook does it, or rather Instagram does it. It's part of the example that we have. So you can see the first pass is, they go from billions is the candidate retrieval to 500 candidates, right? The first pass is a sparse ranker. So it's a very sparse ranker. It doesn't include any of the embeddings. So this sparse ranker, you can think of it as the student model. And then the student model, what is the teacher? The teacher is the final full-fledged model. And we can see this. I wonder if they have an image. Yeah, they don't have an image. Yeah, they don't have an image, but I think this is how they generate this using a student-teacher model, where the student is a smaller, more lightweight model that is trained. Yeah. You can see here the distillation model mimics the combination of the other two stages with minimal features. I think this second model is also a lightweight neural network model that is trained based on this final model, this deep network model. So this is an example of Instagram using cascades for ranking, where they have 3 different rankers.
Great. And okay, a few more questions. Let me see. This is a new question coming. So Ahmed again. So the library by Apple, it's a Turing has a simple model designed to run on device, including recommendation use cases, but using classical techniques. He gave a link. So this, I guess, this is just comment, not a question. Do you have any suggestion for ranking for competing objectives?
Competing objectives, what do you mean? Like such as ranking for conversion versus revenue versus click-through rate? I would say that the main thing that you want to do is to discuss with your stakeholders to make sure that you know, to make sure that they know what they want. So this is a great example. So Alex is a data scientist at Grubhub. So he shared that in his case, he had 2 stakeholders that wanted to maximize conversion and revenue, right? So he thought that he could just find some good trade-off. So it turns out some people prefer conversion, whereas other people prefer revenue. So you can think of it this way. Maybe your growth team might prefer conversion, right? Because the more conversions, the more new users you have, the better. Whereas your commercial team or your chief finance officer might prefer revenue, because it's okay, we don't need all these small, we don't need all these one-off customers who use a lot of vouchers and buy something, but actually not very good revenue in terms of long lifetime value, and we want to optimize revenue. So one way is to focus on this. The other approach I've seen is multi-objective models that you can use to optimize both conversion and revenue, but it's not easy to use those. I haven't seen those used with strong results.
Okay, next one coming actually from India. So how would recommender system work if user is searching each and every items from each category? Example, 1 item each from the given 9 categories, 1-to-1. So is
are you saying that so is this a real user?
So I guess Sankit, if you can comment, or I don't know how you're unable you. I don't know where you are. So
okay, I mean, let me try to answer it. How would this happen theoretically? So let's say if a user is clicking on 1 item from groceries, books, fashion, electronics, what our recommender would do is that we would think that, hey, this user has a wide range of interests, right? And we would recommend him recommendations based on that. Nonetheless, we would also try to learn based on the recency of his clicks and assume that the item that he clicked on most recently, maybe let's assume that the last category he clicked on is furniture. We will assume that that's what he's most interested in and recommend him results with a stronger preference for furniture.
Okay, the next 2 questions are general question. The first one is you mentioned that there's a Google rule for machine learning. Is that a book or is it a website? Some people, Dave asking that.
Yeah, here you go. Rules of machine learning. And let's talk about position bias. Yeah, so rule number 36, avoid feedback loops with positional features. So they talk about, hey, you train your model with positional features and it learns to weigh, I don't know, first position heavily. Your model then gives less weight to other factors for example, where position is true. So then at serving, you you set this position feature to null, or you set this position feature to true for all your items. So what this means is that the model is going to rank all these items equally, regardless of their position. And that's how you sort the order, and that's how you address for positional features. You can just Google for Google rules of machine learning and it should show up.
Yes. The next question coming from Benjamin from Germany, and he said, do you have any thoughts about whether the GraphQL will play a broader role in such a search recommendations stacks? A stack has a technical layer in the future.
Do you mean, so you mentioned GraphQL, do you mean knowledge graph in general, or do you mean graph query language?
GraphQL is the API, I think like a Netflix, wrote about how they use it. It's like an API layer.
Yeah, I'm not certain about that. I know that there are some. I've seen some implementations that use more and more knowledge graphs. To use this, I know Google does this a lot. We've seen how Uber and DoorDash use graphs as well. I'm not sure, honestly speaking, about how we would play out. It is one approach, but it's not very commonly used.
Okay, any other questions? They get a chance. Eugene here can answer all kind of questions. Okay, there's one more. Oh, I keep say, all right, thank you. So, okay, so that's it. Thanks.
All right, that's it.
All right, let's see. So some people comment great talks from Michael. Yeah, thank you, Eugene. Great talks, Eugene, as always. And I mean, you have this deep knowledge, and with all the things you write, all the things you read, and all the experience you have done. So, I mean, thank you so much for the great talks. Thank you for everyone for coming to join the talk from all around the world, and see people from all around the places. Thank you. We'll share the recording later. I mean, Eugene, if you're okay with you can share the slides with me, and I can post it on the meetup so that people can reference. And then the YouTube recording, once we process it, we'll share it with everyone as well.
I'll do that. Let me upload the slides to SlideShare, and I'll send you a link.
Okay, great. Thank you so much.